Hello everyone. Today we will begin the third module of this subject, that is embedded systems. Before we move on to the syllabus, let us just see what embedded systems mean. So what is an embedded system? To keep it in simple terms, embedded system is a system where hardware is embedded with software. And in case of an embedded system, the software is developed by the firm or the manufacturing company, and hence it's called firmware. So it's a combination of hardware and firmware, and which is designed to do a specific task. In contrast to the general computing systems, embedded systems have customized hardware and software along with memory, and they do a specific task. Unlike the general purpose computing systems, embedded systems are designed to do a specific task. So where do we use these embedded systems? Rather, the question should be where we do not use embedded systems. Because embedded systems are used everywhere in our day-to-day lives. Right from the mobile phone that you're holding in your hand to the complex space rovers and spacecraft, embedded systems are there everywhere. So you can take examples of mobile phones or your ATM machines, washing machines, traffic light signal controllers, automobiles, air conditioners, modems or routers or switches, your medical instruments like oximeters, heartbeat monitors, then smart devices like smart watches or smart shoes, then robotics, robotic toys, then in spacecraft and even space rovers. So embedded systems might be an independent system, or they might be a part of a larger system. If you take an example of automobiles, there might be multiple embedded systems, which is a part of a larger system. So there might be embedded systems for headlamp controller or wiper controller or steering control or ABS, anti-braking systems. So this way, in a larger system, there might be multiple embedded systems. Now let us have a look at what we have in the syllabus. So in this module, we have four things to study along with embedded systems. We have sensors and interfacing, and also actuators and communication interface. In embedded systems, we are going to study what it means, the definition of embedded systems, and comparison of embedded systems versus general computing systems, classification of embedded systems, then major applications of embedded systems, then elements of an embedded system, the core of the embedded system, and certain differences between microprocessor and microcontroller, between two types of architecture, that is RISC and CISC architecture, and Harvard and von Neumann architecture. And in sensors and interfacing, we are going to study instrumentation and control systems, transducers and sensors. Then actuators, we are going to study LED, that is light emitting diodes, 7-segment LED display, stepper motor, relay, piezo buzzer, push button switch, and keyboard. And among communication interfaces, we are going to study UART, that is universal asynchronous receive transmit, parallel interface, USB, that is universal serial bus, and Wi-Fi and GPRS. So coming to the textbooks, there are two textbooks to refer. One is Introduction to Embedded Systems, the second edition textbook by Shibu KV, and another one is Electronic Circuits, the Fundamentals and Applications, the same book that is there for most of the syllabus, that is first and second modules. It's the same textbook that is by Mike Toole. The majority of this module is covered in the first textbook, that is Introduction to Embedded Systems, and some part is covered in the Electronic Circuits by Mike Toole. So first we will see what is an embedded system. An embedded system, according to the textbook definition, this is the definition of an embedded system. It is an electronic or electromechanical system designed to perform a specific function and is a combination of both hardware and firmware. So to keep it in simple terms, embedded system is something where hardware is embedded with software. And here the software is manufactured by the firm or the manufacturing company. That's why it is called firmware. And most of the embedded systems, almost every embedded system is designed to perform a specific function. So every embedded system is unique, and the hardware as well as the firmware is highly specialized to the application domain. That means it is customized hardware and software, and it is for that particular function only. So an embedded system which is designed for one application domain cannot be used for some other domain. So it is application or domain specific in nature. So there is a differentiation or distinction between embedded systems and general computing systems. So when the computer revolution began, it was with the general purpose computing systems. So first the systems used were general purpose computing systems. Later it was realized that the general computing requirements were not sufficient for the embedded computing requirements. So there has to be something special. The embedded computing requirements demand something special in terms of response to stimuli or meeting the computational deadlines or the power efficiency or limited memory capability and other things. So they have to be little faster in response, and not just that, it has to be more efficient, power efficient, because most of them are battery operated systems. Then it has to meet the computational deadlines, and also the memory requirements are different than what we have in general purpose computing systems. So this gives a brief differences between general purpose computing systems and the embedded systems. So we will see these differences one by one. General purpose computing system, it is a system which is a combination of generic hardware and a general purpose operating system for executing a variety of applications. So we use a generic hardware, not a customized or a tailor-made hardware, and a general purpose operating system like a Windows maybe for executing a variety of applications. It is not application specific. Uh, we use the general purpose as the name itself suggests. It is used for general purpose, so for executing a variety of applications. When it comes to embedded system, it is a combination of special purpose hardware and an embedded operating system for executing a specific set of functions. So not all functions or not all applications, only a specific set or one specific application. General purpose computing system, it contains a general purpose operating system, whereas embedded system, it may contain an operating system or may not contain it sometimes, but when it contains an operating system, it is an embedded operating system. In general purpose computing system, the applications are alterable or it is programmable by the end user. So that is, it is possible for the end user to reinstall the operating system and also to add or remove the user application. Just like in your computer, you can reinstall your operating system like installing Windows, and you can add or remove different user applications. Whereas in case of embedded system, the firmware of the embedded system is pre-programmed by the manufacturer itself, and it is not alterable by the end user. So there may be exceptions for some systems supporting OS kernel or image flashing through special hardware settings. In case of general purpose operating systems, general purpose computing systems, the performance is the key deciding factor in selection of the system. That means faster is better. It's always the performance and not the things we are bothered about. Whereas in embedded system, application specific requirements, apart from performance, we also look for power requirements, memory usage as the key deciding factors. The general purpose computing system, they are less or not at all tailored towards reduced operating power requirements or options for different levels of power management. So that means there are no different options for managing or reducing the power. Whereas in case of embedded system, it is highly tailored to take advantage of the power saving mode supported by the hardware and the operating system. So now we normally have sleep mode, deep sleep mode, and different modes to save power in case of embedded systems. General purpose computing systems, here the response requirements are not time critical, whereas in case of embedded systems for certain category like mission critical systems, the response time requirement is highly critical. So that is, it has to be highly responsive system. In case of general purpose computing system, it need not be deterministic in execution behavior. Deterministic means we will know in advance what it is going to do. Whereas in case of embedded system, the execution behavior is deterministic. For certain types of embedded systems like hard real-time systems, we should exactly be knowing at what time what is going to happen. This is about the differences between the general purpose computing system and embedded system. Then we have classification of embedded systems. So embedded systems, they can be classified based on different criteria, like based on generation, based on complexity and performance requirements, based on deterministic behavior, or based on triggering. Okay, the first criteria is based on generation. Based on generation, we have four generations actually: first generation, second generation, third generation, and fourth generation. And what is going to come next is the next generation. In the first generation, the early embedded systems, they were built around the 8-bit microprocessors like 8085 and 4-bit microcontrollers. Okay, 8085 and Z80, they are 8-bit microprocessors and 4-bit microcontrollers. They were simple in hardware circuits with firmware developed in assembly code. So simple applications like digital telephone keypads or stepper motor controlling units. So these are all the examples for first generation embedded systems. Coming to the second generation, the embedded systems, they were built around 16-bit microprocessors and 8-bit or 16-bit microcontrollers, a little more advanced than the first generation. The instruction set were much more complex and powerful than the first generation. Some of the second generation embedded systems contained embedded operating system for their operation. So they had an operating system. The first generation did not have any operating system. It was just a code in assembly language. Whereas in second generation, some of them included an embedded operating system. So normally second generation embedded systems, the examples are data acquisition systems or SCADA systems. SCADA stands for supervisory control and data acquisition. So which are used in control systems in industrial applications. The third generation, here the embedded systems are built around 32-bit microprocessors and 16-bit microcontrollers. The application and domain-specific processors or controllers, like digital signal processors and application-specific integrated circuits, they came into picture. Apart from microprocessor and microcontroller, DSPs and ASICs, they came into picture. The instruction set of processors, they became more complex and powerful, and the concept of instruction pipelining also came into picture. You know what is instruction pipelining? When present instruction is being executed, the next instruction can be fetched so that the instruction execution speed can be increased. Okay, the dedicated embedded real-time and general-purpose operating systems entered into the embedded market. So the embedded system spread its ground to areas like robotics, media, industrial process control, networking, and others. So these are the applications of or the examples where third generation embedded systems are used. Next generation or the present generation, what we have is the fourth generation of embedded systems. Yeah, the advent of system on chips, SoC, or the SoC, that is a chip which can be used as a computer, that is system on chip. Then reconfigurable processors and multi-core processors, where the processors have more than one core or a parallelism is achieved. They came into picture, which bring in high performance, tight integration, and miniaturization into the embedded device market. So the performance is increased. Tight integration means more number of devices are integrated in a particular area, and the size of the embedded system is becoming smaller and smaller. The SOC technique, it implements a total system on a chip by implementing different functionalities with the processor core on an integrated circuit. That means along with the processor, we have the entire system on a single chip. That is called system on a chip. So these make use of a high performance real-time embedded operating systems for their functioning. The examples are smartphones or mobile internet devices and other advanced embedded systems. So what is going to come next? That is the next generation. The processor and embedded market is highly dynamic and it is more demanding. So day by day, demands are growing, and the next generation embedded systems, they are expected to meet these growing demands in the market. So this is about the classification of embedded systems based on the generation. Next classification is based on complexity and performance. So based on complexity and performance, we have three types of embedded systems. That is small scale embedded systems, medium scale embedded systems, and large scale embedded systems or complex systems. The small scale embedded systems, they are simple in application needs, and the performance requirements are not time critical. Okay, so they are very simple in applications like an electronic toy. The performance is not time critical. That means when you press a button, something happens, right? Or something like that. Or very simple in application. So it is usually built around low performance and low cost 8-bit or 16-bit microprocessor or microcontroller. It may contain an operating system or may not contain an operating system for its function. It is a very simple embedded system. Next, we have medium scale embedded system. Here it is slightly complex in hardware and firmware or software requirements, complex compared to small scale. It is normally built around medium performance, low cost 16-bit or 32-bit microprocessor or microcontroller, or maybe digital signal processors. So they usually contain an embedded operating system for functioning. It may be a general purpose operating system or a real-time operating system. Then we have large scale embedded systems or complex systems. They are highly complex in hardware and firmware or software requirements. So they are employed in mission critical applications demanding high performance, where timing requirements are very critical. So they are usually built around high performance 32-bit or 64-bit RISC processors or controllers or reconfigurable system on chip, or multi-core processors and programmable logic devices. So they have, so we normally use RISC like ARM microcontroller or microprocessors, that is reduced instruction set computing, and multi-core processors, where the processors have more than one core and parallelly things can be executed. So they may contain multiple processor or controllers and core units or hardware accelerators for offloading the processing requirements from the main processor of the system. That means hardware accelerators, like in case of DSP, while if you use a DSP and all, so these things can be achieved by using the hardware. Some software instructions can be accelerated. If you want to execute a particular task using software, so it takes more time because you will have to write a more lines of code and then execute it, then decode it and then execute it. But instead, if a hardware is provided for that, so it will speed up the task. If an additional hardware is provided, it will speed up the task. Then decoding or encoding of media, like images or videos, cryptographic function implementation. These are all examples of processing requirements which can be implemented using a coprocessor or hardware accelerator. So usually they contain a high performance real-time operating system or RTOS for task scheduling, prioritization and management. These are some functions of operating systems. So this is about the classification of embedded systems based on complexity and performance. So we have small scale, medium scale and large scale embedded systems. Then there is classification based on deterministic behavior. So based on deterministic behavior, this is applicable for real-time systems. The real-time systems are those where time response is very critical. The application or task execution behavior, it can be either deterministic or non-deterministic. Deterministic means we know what is going to happen, what will be the outcome. Non-deterministic means we may not know what is going to happen next or at what time what is going to happen. So based on the execution behavior, the real-time embedded systems, they are classified into hard real-time and soft real-time. Hard real-time are the systems where the timing response is very, very critical and it cannot miss a deadline at any time. Whereas soft real-time systems, they are also very time critical, but if there is a small miss in the deadline or if there is a very small delay, it can be tolerated. Examples for hard real-time systems are, you can take examples of flight control systems or spacecraft monitoring systems, space control systems, where a small miss in the deadline, even by some microseconds, can cause a huge loss to life and property. So if there is a small delay in the flight control system, there might be a huge loss in life or property. Whereas soft real-time systems are systems like in ATM. If there is a small delay, even though the time response is very critical, it has to happen in real time. But if there is a very small delay, like in some seconds or 1 minute or something like that, you can tolerate, and nobody is going to die in such cases, but you can tolerate and still the system will work. Next classification is based on triggering. Based on triggering, we have event triggered or time triggered. These are for embedded systems which are reactive in nature. That means for some action, embedded systems will react. So like for process control systems in industrial control applications, they are classified based on the trigger. So it can be event triggered or time triggered. Event triggered means the embedded systems, they are triggered when particular event happens. Okay, whereas time triggered systems, they triggered at a particular time or particular interval of time. Next, we have some major application areas of embedded systems. So embedded systems, they are used everywhere in our day-to-day lives or even in different applications. These are some major areas. That is, we have in consumer electronics, like in case of camcorders, digital cameras, and other things, video recorders. In household appliances like televisions, DVD players, washing machines, refrigerators, microwave ovens, and other examples. Then home automation and security systems like air conditioners, sprinklers for your gardens, intruder detection alarms to detect an intruder, then closed circuit television or CCTV cameras, fire alarms or fire detectors. These are all examples for home automation and security. Then coming to automotive industry, we have anti-lock braking systems or ABS in the automobiles, engine control, ignition control, transmission control, automatic navigation systems based on GPS, right? These are all examples for automotive industry. In telecom, we have cellular telephones, telephone switches, handset multimedia applications, and other things. In computer peripherals, maybe like printers, scanners, fax machines. In computer networking systems like network routers, switches, hubs, firewalls, etc. In healthcare, that is all the different kinds of scanners you have, including CT scan, other things. Then EEG, that is electroencephalogram, that is used to detect the activities of the brain. Then ECG, that is electrocardiogram for activity of the heart, and different measuring instruments like oximeters, which are presently used to measure the oxygen saturation level, or maybe your blood pressure monitor or blood glucose monitor, and other embedded devices. Then coming to measurements and instrumentation. So here we have digital multimeters, digital CROs, logic analyzers, PLC systems, and other things. So PLC stands for Programmable Logic Controller. We use them in measurement and instrumentation applications. Then coming to banking and retail, we have ATM machines, automated teller machines, or currency counters, which you might find in banks or other places of business. Then point of sales are where these are some devices which you might find in shops or in petrol bunks where you swipe your ATM cards for payment. Then card readers like barcode readers, RFID readers, smart card readers, handheld devices. So these are all examples for card readers. Then some wearable devices. You have like health and fitness trackers, smartphone screen extension for notifications. So these are all examples for wearable devices like your smart watches or like Fitbit and other things. Then you also have cloud computing and Internet of Things. These are new upcoming applications of embedded systems. So in the next class, we will see some other things like purpose of embedded systems and the elements of embedded systems. So we'll stop for today.